In a fraction of a second, the universe expanded rapidly, like a balloon inflating at an incredible speed. As it expanded, it cooled, setting the stage for everything we see today. This wasn't chaos, though. The universe, even in its infancy, followed laws of physics. These laws would govern the creation of everything from tiny particles to vast galaxies. We can still detect the faint afterglow of the Big Bang today. It's called the cosmic microwave background radiation. Think of it as the first light ever emitted in the universe, now stretched and faded after traveling for billions of years. It's a cosmic baby picture, a glimpse into the universe's earliest moments. The Big Bang is a mind-blowing concept, but it's the foundation for everything that exists, including us. As the universe cooled after the Big Bang, energy started to transform into matter. This wasn't the kind of matter we see around us, not yet. These were the tiniest building blocks of everything, the fundamental particles. Imagine a chaotic soup of particles colliding at unimaginable speeds. These particles included quarks, leptons, and bosons. Over time, the universe cooled enough for quarks to come together. They formed protons and neutrons, the particles found in the heart of every atom. This was a crucial step. It paved the way for the formation of atoms themselves, the building blocks of all matter. The universe, at this point, was still a wild place. Photons, the particles that make up light, were constantly interacting with these newly formed protons and neutrons. It was a dense, hot, and opaque fog of particles. But within this fog, the seeds of structure were being sown. The universe was preparing for its next grand transformation, the creation of the first atoms. The universe continued to expand and cool. Finally, about 380,000 years after the Big Bang, something amazing happened. Electrons, those negatively charged particles, began to combine with protons and neutrons. This created the first atoms, mostly hydrogen and helium, the two simplest elements in the universe. This event was a turning point. With the formation of atoms, the universe became transparent. Photons, no longer constantly bumping into free electrons, were free to travel across space. The universe, once a murky fog, was suddenly filled with light. The light from this era still travels through the universe today. It's what we detect as the cosmic microwave background radiation. This radiation is incredibly uniform, but it contains tiny fluctuations. These fluctuations, like subtle ripples in a pond, represent the seeds of the large-scale structures we see in the universe today, like galaxies and galaxy clusters. Gravity is the architect of the universe. It pulls matter together, sculpting it into larger and larger structures. In the early universe, gravity began to pull together the vast clouds of hydrogen and helium gas. These clouds, denser in some areas due to the tiny fluctuations from the Big Bang, became the birthplaces of stars. As gravity pulled the gas inward, the clouds began to spin. The centers of these spinning clouds grew hotter and denser. Eventually, the pressure and temperature at the cores became so intense that nuclear fusion ignited. Stars were born. These early stars were massive and short-lived, but they played a crucial role in the evolution of the universe. They produced the first heavy elements, heavier than hydrogen and helium, through nuclear fusion in their cores. And when these stars exploded as supernovas, they scattered these elements throughout space. This enriched the interstellar medium, the gas and dust between stars, with the ingredients needed for the next generation of stars and, eventually, planets. Section 5. Forging elements. Cosmic alchemy. Stars are incredible cosmic furnaces. Deep within their cores, they fuse hydrogen atoms into helium, releasing enormous amounts of energy in the process. This nuclear fusion is what makes stars shine. But stars don't stop at helium. As a star ages and uses up the hydrogen in its core, it begins to fuse helium into heavier elements like carbon, oxygen, and nitrogen. The more massive the star, the heavier the elements it can forge. This process of element creation is called nucleosynthesis. These heavier elements are essential for life as we know it. Think about it. The carbon in our bodies, the oxygen we breathe, the calcium in our bones. All of these elements were created billions of years ago inside the cores of stars. We are, quite literally, stardust. Section 6. Supernova Spectacular. Scattering the seeds of life. Massive stars live fast and die young. When a star significantly larger than our Sun reaches the end of its life, it explodes in a spectacular supernova. This is one of the most powerful events in the universe. For a brief time, a supernova can outshine an entire galaxy. Supernovas are essential for the evolution of the universe. The intense heat and pressure of the explosion can create elements even heavier than iron, such as gold, silver, and uranium. More importantly, supernovas scatter all the elements forged in the star's core, including the building blocks of life, out into space. These elements enrich the surrounding interstellar medium, seeding the formation of new stars and planetary systems. So, in a sense, we owe our existence to these stellar explosions. In Section 7, Birth of our Sun, a Star and its System. About 4.6 billion years ago, in a quiet corner of the Milky Way galaxy, a cloud of gas and dust began to collapse under its own gravity. This cloud, enriched by the remnants of countless supernovas that came before, contained all the elements needed to form our solar system. As the cloud collapsed, it began to spin faster and faster, forming a rotating disk of material. At the center of this disk, the material clumped together, eventually becoming so hot and dense that nuclear fusion ignited. Our Sun was born. The remaining material in the disk continued to swirl around the newborn Sun. Over millions of years, particles in this disk collided and stuck together, gradually growing larger. These clumps of matter eventually formed planets, moons, asteroids, and comets. Section 8. Earth's formation, from dust to our home. In the early solar system, Earth formed from the gradual accumulation of dust and gas. This process, called accretion, started with tiny particles sticking together, eventually forming larger and larger bodies. As Earth grew, its gravity attracted more and more material. The energy from these impacts, along with heat from radioactive decay within Earth's interior, melted the planet's core. Over time, denser materials like iron sank to the center, while lighter materials like silicate rocks rose to the surface. This differentiation created Earth's layered structure, a solid inner core, a liquid outer core, a mantle, and a crust. Volcanoes erupted, spewing gases from Earth's interior into the atmosphere. Eventually, Earth cooled enough for liquid water to exist on its surface, setting the stage for the emergence of life. Section 9. The universe expands, a never-ending story. For centuries, astronomers believed that the universe was static and unchanging. However, in the 1920s, Edwin Hubble made a groundbreaking discovery. He observed that galaxies are moving away from us, and the farther away a galaxy is, the faster it's receding. This observation led to the development of the Big Bang Theory and the realization that the universe is expanding. But the expansion of the universe isn't like an explosion where everything flies apart into empty space. Instead, space itself is stretching, carrying galaxies along with it. Imagine dots on a balloon. As you inflate the balloon, the dots move farther apart. But they're not moving across the surface of the balloon. The space between them is expanding. And here's where things get even more interesting. In the late 1990s, astronomers made another startling discovery. The expansion of the universe is accelerating. This acceleration is thought to be driven by a mysterious force called dark energy, which makes up about 68% of the total energy density of the universe. Section 10. Modern astronomy unveiling cosmic secrets. Today, astronomers use incredible tools to study the universe. Powerful telescopes on Earth and in space capture light from distant galaxies, revealing their properties and movements. Spacecraft explore our solar system, sending back stunning images and data about planets, moons, and asteroids. These observations have allowed us to piece together the history of the universe and understand its evolution. We've discovered new planets, orbiting other stars, some of which may have the potential to support life. We've detected gravitational waves, ripples in the fabric of space-time, confirming Einstein's predictions and opening a new window into the universe. Section 11. A journey unfolds, our place in the cosmos. From the Big Bang to the formation of stars and galaxies, from the creation of elements to the birth of our solar system, the universe has been on an incredible journey for billions of years, and we are fortunate to be a part of this unfolding story. Our understanding of the universe is constantly evolving as we make new discoveries and refine our theories. There is still so much we don't know, from the nature of dark matter and dark energy to the possibility of life beyond Earth. As we continue to explore the cosmos, we gain a deeper appreciation for the vastness and complexity of the universe. We are reminded of our place within this grand cosmic scheme, a small but significant part of something truly awe-inspiring.